Next speaker will be Hans Juergen, and they will tell you something how he extended XPath to cover not only the XML trees, but some other structures.
Thank you. Can you hear me well? Okay. The main purpose of XPath is to navigate through the contents of XML documents. And FOXpath is an extended version of XPath supporting a navigation of the file system which feels and looks like the navigation of XML data. And today I will talk about a generalization of FOXpath, adding support for virtual file systems like archives, NoSQL databases, and repositories. Tree-structured information is ubiquitous. Tree structure organizes the contents of many resources. Think of XML, HTML, JSON, CSV. But tree structure also organizes the contents of many resource systems, the file system, archives, repositories, NoSQL databases. So how do we use these trees? How do we find in them what we need? Dealing with XML documents, we have XPath, an expression language for navigating content trees. A simple example reminds you of the extraordinary power and elegance of XPath. Navigation is viewed as a pipeline of steps. We have several navigation axes at our disposal. We can formulate predicates and therefore achieve a filtering to any degree of detail. This example traverses rather complex data about flights and gives us the dispatchal airports of evening flights to New York City. Usually one would have to program to achieve this result, but with XPath we just say what we want. We are kings. We express. And please do not forget that XPath is by no means restricted to XML documents. Many data formats can be passed into node trees and thus be made accessible for XPath. And that's the reason why I'm really profoundly excited by what Stephen Pemberton is doing. So how about the file system? We have APIs, we have no expression language. Although APIs are by far inferior to an expression language like XPath. If you think differently, make a mild experiment. Don't use regular expressions anymore. Only use APIs with functions like starts with, ends with, contains. So this situation motivated me to create the FOXpath language, which enables a navigation of the file system, which looks like the navigation of XML data. An example shows the similarity. Again, a pipeline of steps, navigation axis, predicates, the things we're used to. But it's navigating the file system. But FOXpath also supports the navigation of node trees and the seamless integration of both types of navigation. So the extended example first traverses the file system and then continues navigation within the node trees in the found documents. The path operator of XPath is here represented by a backslash. The slash is used for a new operator, the URI access operator. So FOXpath is a superset of XPath 3, which supports file system navigation. It adds a new expression kind, the URI access step, consisting of a URI access, a URI name test, and optional predicates. Of course, it's a faithful copy of the node access step defined by XPath. And we have a new operator, the URI path operator, which here is represented by a slash. and it combines URI navigation steps into an URI navigation path. Semantic extensions ensure that the integration of file system navigation and node tree navigation is seamless. You can do it elegantly within a single expression. Further extensions are borrowed from XQuery. We have global and external variables, namespace declarations, and a simple flower expression supporting multiple let and for clauses. In order to get a feeling for FOXpath, I want to show you a few examples. I cloned a GitHub project created by the Oxygen people. The project is called User Guide, and I will apply a few expressions to this project now in my file system. So the first expression uses two different navigation axes, and it counts the number of data files. The second expression refines this counting. It adds an attribute excluding all data files found at any level under a folder with the name not_used. The third expression demonstrates the integration of file system and node tree navigation. It again first navigates to all those data files and then enters the node trees which they contain, inspects the local name, and creates a frequency table. Frequencies is an extension function which I added. The final example is a bit more complex. It counts all data files in the user guide projects which are not referenced by an href attribute found in any of the data or data map files. So the first clause finds a list of all data file names. The second clause navigates to all data and data map files, then enters them, visits the href attributes, and extracts the file names. And the return clause gives us the names which are not referenced anywhere. It happened to be 43. So FOXpath adds to XPath file system navigation. But FOXpath is not really aware of the file system as such. It's just dealing with URIs and their relationships. Relationships as they are found in the physical file system, but also in virtual file systems like archives, SVN repositories, GitHub projects, and so forth. So the question arises if FOXpath may also support navigation of these virtual file systems. We need a conceptual framework relating the abstract URI navigation defined by the FOXpath language to an implementation-defined set of logical file system types. And a good starting point is a generalized concept of file systems, which I call a logical file system. It is based on URI relationships which deserve to be treated as a concept in its own right. From a practical point of view, the key abstractions are URI operations and URI dispatchal. URI operations are small building blocks of functionality from which navigation can be composed. These building blocks are generic, and URI dispatchal binds the generic building blocks to specific implementations as adequate for the file system type at hand. Now let's take a closer look at these concepts in turn. What's a logical file system? Loosely speaking, it is a tree of URIs whose leaves can be resolved to content, that means sequences of characters or bytes, and whose inner URIs cannot be resolved to content, but are perceived as mere containers for other URIs. So the generalized notions of files and folders are just the outer and inner URIs of such a tree. Real systems matching this model are the physical file system, of course, but also virtual file systems like archives, document databases, version control repositories, GitHub projects. And later, I will introduce a third type of logical file system in which each resource, folder, or file is described by a distinct unit of information. And due to this direct correspondence, I will use the term literal file systems. So what precisely is a tree of URIs? A tree is based on two relationships, child and parent. And when we are dealing with path-structured URIs, which is a crucial assumption, then it's easy to define what is a child URI and a parent URI of a given URI. A child URI is what you get when you add one more step to the path. The parent URI is what you get when you cut off the final step. So these trivial relationships suffice to formally define a tree of URIs. It's just a collection of path-structured URIs with a common prefix. These relationships also imply URI access, as we are familiar with from XML node navigation, child, descendant, parent, ancestor, and so forth. Okay, a logical file system is a tree of URIs. What do we expect from a URI tree navigator? I should say three things. First, traversal. Second, inspection of basic resource properties, like, for example, the date of last modification. And third, of course, retrieval of content. And all this functionality can be decomposed into small building blocks, small units of functionality, which all amount to mapping a given URI to a piece of information. And these building blocks I call URI operations. This slide shows you the main operations which I identified. First, we have navigation primitives mapping a URI to its child URIs or to its descendant URIs. Then we have operations mapping a URI to content, either unstructured as a sequence, as text, or as a sequence of bytes, or structured, represented by a node tree. And finally, we have operations mapping a URI to basic resource properties, like kind, is it a file or a folder, name, file size, date of last modification. And for each supported file system type, we will have a separate set of implementations of these operations. And such a set of implementations I call a URI processor. So we have, for example, a URI processor for the physical file system. And we have a different URI processor, let's say, for archives. The URI processors depend on backing APIs which enable them to implement the functionality expected from them. And this slide gives you an overview of the major dependencies and their use in the context of different types of file systems. My implementation of the FOXpath language is written in XQuery. Therefore, most dependencies are on XQuery modules, either defined by the XPath initiative or by my XQuery processor of choice, which is base X. For example, the navigation of GitHub projects requires access to the GitHub REST API. And navigation of SVN repositories requires access to the SVN command line interface. So this is maybe the most important slide in this presentation. URI operations provide us with building blocks of functionality from which complex behavior can be composed. At the same time, they provide us with a level of abstraction which hides the specific nature of a logical file system. This slide shows you 3 FOXpath expressions which traverse different types of file system: a physical file system, an archive, a GitHub project. And these 3 expressions happen to use the same navigation step, which is a URI access step using the child access and the name test C*. Generic code translates this navigation step into the invocation of a generic URI operation. Child URIs, input, URI, name, and kind. This operation delegates the actual processing to a special implementation which is appropriate for the file system type at hand, which is recognized by inspecting the input URI. So in the first example, this implementation will be called. In the second, this. In the third example, this will be called. So please think of URI operations as a generic interface exposed by a logical file system of any type, while URI dispatchal binds the generic interface to a specific implementation on a URI by URI basis. URI dispatchal is a crucial operation. The URI is inspected and dispatchal rules are applied. As a result, the URI domain of the URI is determined. URI domain is just a fancy word for an identification of the type of file system at hand. For example, physical file system or archive. And the domain implies the URI processor to be used. This slide shows you the URI dispatchal rules which I used. The rules are applied in order, and the first matching rule wins. So if a URI contains such an archive step, it is identified as a URI from the domain archive, even if it starts with SVN minus, because the archive rule comes first. Okay, so a couple of examples should demonstrate to you this new flexibility which we have now gained by this generalization. Again, I have my Oxygen user guide project, this time as a zip file, and for some reason I'm unwilling to unpack it. Now consider this expression. First, it navigates in the file system to the zip file. Then it enters the archive and moves to the root of the archive. Within the archive, it drives down to all the contained jar files, which are themselves archives. So the expression moves to the roots of these nested archives, and then within these nested archives, down to all the XSL files. These are XML documents, so it enters a node tree and drives down to all match attributes and builds a sorted list of distinct values. So it's a single expression performing a 4-phase navigation: file system, archive, nested archive, node tree. The second example demonstrates navigation of an SVN repository. I selected the Xalan repository from the Apache Foundation. And I was curious. I wrote this expression, driving down to all XSL files, entering their node trees, extracting the version, and constructing a frequency table. Only version 1. Okay, an interesting extension of our notion of file systems consists in literal file systems. A literal file system is a collection of folders and files, each one of which is described by a distinct entity of information called a resource descriptor. A resource descriptor associates its resource with a navigation URI, and these navigation URIs taken together arrange all these resources neatly in one tree ready for navigation. So a resource descriptor is nothing else but a record of metadata describing a file or a folder. The key properties are, oh, sorry, I forgot to mention something. I defined 2 data formats for creating literal file systems. UTREE, which is XML-based, and UGRAPH, which is RDF-based. So a resource descriptor defines a folder or a file, and there are 2 key properties, a navigation URI and a retrieval URI. And by concept, these are distinct properties. They may have the same value, but they need not. And this means we can impose a logical structure in our literal file system, which is completely independent of any physical structures. For example, a literal file system might take a large collection of totally unrelated internet addresses and arrange them neatly in a tree ready for XPath navigation or FOXpath navigation. So this slide gives an impression of a RDF-based resource descriptor. It's in turtle format, the triples, and note that the retrieval URI and the navigation URI are different. The navigation URI places the file within the GitHub project as we as humans perceive it. And the access URI is, the retrieval URI is what is used to actually retrieve contents using the GitHub REST API. Literal file systems are not created by hand, but by tools. And the FOXpath implementation ships with the tool for creating UTREE or UGRAPH descriptions of GitHub projects or SVN repositories. So, for example, with this command, simple command, I get a UTREE description of all GitHub projects created by Oxygen, which happen to be 38. If you use the UGRAPH format, you get a turtle file, and then you would have to take 2 further steps, shove them into a database and publish them as a Sparkle endpoint, but this can be done with 2 simple command line calls. Okay, when you have created your literal file systems, you can navigate them as if the resources which they describe were part of your local file system. Note the options T and G, which pass crucial information to the URI dispatcher, which of course has to be informed about the UTREEs or UGRAPHs to be considered. So, a couple of examples. I created now this UTREE description of all the Oxygen projects, and the first expression gives me the number of lines of all XSL files found in all 38 Oxygen projects. It's 83,000. The second example gives me the number of Oxygen projects which do contain XSL files. It is 15. And the last example demonstrates again the mixing of file system and node navigation. It gives me the names of all Oxygen projects hosted by GitHub, which contained XSL files with a version greater 2. In other words, Oxygen projects using XSLT3. This query takes a minute or something because a vast amount of code has to be retrieved on the fly via the GitHub REST API. But then I get the answer. Currently, there are 2 Oxygen projects using XSLT3. The last example should give you an idea of the scale one can achieve. Again, I used this command line tool to get a UTREE description of all Google projects at GitHub. And I wrote this little FOXpath expression giving me some basic statistics. How many projects, how many files, how many XSL, XSD, XSL files, and drumbeat, what is the frequency distribution of the XSLTs at Google. These are the results. 901 projects, over 500,000 files, 8,000 something XML, 80 XSD, 44 XSL, 2 of which are not well formed, and the rest XSLT1. So let me summarize the scope of URI navigation currently supported by FOXpath. It's physical, virtual, and literal file systems. Virtual means archives like zip, jar, EPUB, and so on. SVN repositories, BaseX databases, and GitHub projects or sets of GitHub projects, but GitHub requires a description via UTREE or UGRAPH. And finally, any UTREE or UGRAPH literal file system. So what are the main points of my talk? First, FOXpath gives you a single navigation model covering URI navigation and node navigation. And it offers you a seamless integration. You can combine them within a single expression. It is important to understand that URI navigation is based on the key concepts of URI operations and URI dispatchal. The scope of supported file system types is not defined by the FOXpath language. It is implementation defined and easily extensible. All you have to do is add one more URI processor and add one more URI dispatchal rule. That's it.
So we still have time for questions before we will navigate ourselves to lunch. So I'm almost blind after the, over there, George, at the top. So please mic to him.
Thank you, George Bina from Oxygen XML. It was quite interesting to see, and I have just one question regarding the use of backslash for the XPath navigation. I was thinking maybe using a separator, like a bank operator, let's say, that delimits the path from the XPath, from the content navigation. Have you considered such an alternative or something like that?
I did not. Thank you for this question. I'm glad that you asked. It's completely configurable. In fact, I did not mention that the canonical syntax, which I do not use myself in my practice, uses the slash as it is used in XPath and so on. So it's just configuration data, which character to use for the node path operator, which character to use for the URI path operator. It's not part of the language as such.
Sounds like SGML declaration to me.
Pardon?
It looks like SGML declaration where you can change those characters. Okay, and then Liam had some question as well, I think.
Yeah, Liam Quinn, W3C. It's great to see this is the second talk I've seen about FOXpath, and it's interesting to watch the development. One of the things that it reminds me of this time, more than last time in fact, when I seem to remember I also asked about the backslash, is years ago there was a language called web query, which nothing to do with WebQL that became XQuery and was for XML, but rather was a query language for asking questions like, find me all documents that are at the same level in the hierarchy as this one. The kind of things you're asking. And I can probably find information about it, but you might get a lot of ideas from that, and it's great to see that kind of web querying happening again. Thanks.
Mm-hmm. Thank you.
I think Gerrit has a question as well.
Yeah, Gerrit Imsike, LETich. Have you considered using XML catalogs for these file system path mappings that can be configured via triples?
Yeah, as a matter of fact, I didn't use the word, but it is a literal file system is just a catalog. Yeah? No, I have not considered using an existing format because I think it's maybe wrong. It's not giving me quite what I need, especially also as I think that I'm going to extend the possibilities of what to put into it. But maybe it is something to consider. Yeah.
Okay, so I don't see any other questions, so thank you very much again. And of course, there is lunch now, and we will meet here in this room 20 minutes before 3 o'clock, and we will continue with few other sessions before we will end today.